Hi, this is Jeff Coronado on behalf of JCSE, and this is Bridging the Gap. So this is a series of tutorials that we have here in the office to assist young engineers, both engineers that are still maybe in school, just trying to looking to get a head start on their structural engineering career, trying to get themselves lined up. Obviously, it's very competitive to get structural engineering positions when you're coming out of school. So maybe you're looking to get a head start, or you've been at it and you're still within your first few years after school. And yes, it's somewhat overwhelming to make that transition from what you learned in school to what practice actually expects you to know. So in an effort to assist you with that, we've got this series of structural engineering design tutorials. So with that in mind, let's jump into this. In particular here, the title for today is Connecting a Beam That's Embedded in an Exterior Wood Stud Wall. And we'll get into the purpose of this in a second, but for right now, let's just be mindful of the detail this is. This is WW6B, that's our identification. So if you are looking for any other tutorials that are kind of related to this one, that maybe cover different aspects of the concepts involved here, you might also want to look in our library for WW6B and see if you find other associated tutorials related to what we're going to be talking about here. But in particular, we're looking at how to anchor a beam that is stiffening an exterior stud wall. So let's get into a plan view here. Clear the screen. Let's get into a plan view. So here we have a floor plan. It's a type 5 structure. It can be 2 stories or more. What we have here is floor area. So all of this is floor. All of this is floor. We would have an exterior wall across here, and then we have an opening in the floor, in the diaphragm, right here. So now this is very frequently we would have a stairwell. Could also be an elevator or just some other opening that occurs in the floor right adjacent to the exterior wall. The problem with that floor there, with that opening there, is that it introduces a weakness in the wall. It makes it unstable. We're not going to get too much into that because that's a matter for another tutorial. By the way, if you have a question on that or anything else that I say here, feel free to leave us a note at the end and we'll try to point you in the right direction. There's likely other tutorials that we have in the library that cover some of these other issues that you may be wondering about. So by all means, feel free to leave us a note afterwards and we'll try to point you in the right direction. But we don't want to get too much into this opening and the effects that it causes. Because again, that's covered in another tutorial. Let me see if I can clear the screen here. The important thing for now is to understand that because of that weakness that stair introduces, we will likely introduce a beam in the wall, embedded in the wall, that bridges the gap for that opening. That way, the problem that we have here is that we are going to have a wind force, what we call a component and cladding wind force, which acts out of plane of the wall, and that's all covered in other tutorial sessions. So just feel free to ask if you need some direction with that. But we have wind pressure that exerts a suction force on the wall, wants to pull the wall out. So we introduce this beam that we're showing here in red to kind of strengthen the wall and stiffen the wall across the diaphragm opening. Now, also remember that we do have floor framing. So I'm not going to show, well, I'm going to show a little bit here, but let's assume we've got floor joists running in this direction. So I'm going to illustrate maybe a couple of the floor joists as they run left to right. Okay, so there's our floor joist. We've got the beam in red that's intended to resist the out of plane force in the wall. Now the problem is now that we've got this beam that bridges the gap in the diaphragm, how do we anchor the beam so that it doesn't blow out, right? Like what keeps this beam, let's say, from just kind of floating out here, right, and just blowing out? Okay, well, what keeps it from blowing out is we need to provide an anchoring force that pulls the beam at each end back into the diaphragm. So how do we do that? Well, the way we're going to do that is by providing first a strong element, let's say a beam, at each end of the opening. Now remember, that opening was, the opening in the diaphragm was right here, right? So at each end, top and bottom of that opening, we're going to provide a strong element that not only helps support the stairs, but also pulls back the beam that we're showing in red from to keep the beam from blowing out. Okay, so that's kind of the purpose there. Now, the trick here is, what we need to focus on here is how do we anchor that beam so that it doesn't blow out? Right? What keeps that beam from blowing out? What keeps the end of that beam from blowing out? So what we've got shown here is that connection that keeps the beam from blowing out. So that's what we want to focus on now. So let me clear this screen and move on. Okay, and this is what that's going to look like. So the beam that we had in red, the one that's embedded in the wall, is this one here. That's this beam. So our forces, our wind pressure is acting in this direction. So our wind is trying to create a suction force on the wall, causing the beam to pull out and away from the structure. So what we need to do is to provide a force, a transfer at each end of that beam that pulls the beam back into the structure. This is the element that's parallel to the framing of the floor, right? This is where we had additional floor joists. Now we're looking at them going from top to bottom, right? And then the exterior wall, remember the exterior wall just kind of continues across here. Okay, so now with that, hopefully that's clear. Again, anything that isn't clear, by all means, feel free to leave us a note at the end and we'll try to point you in the right direction or clarify for you. But with that in mind, now let's clear the screen and let's look at this connection. So again, we've got a force here that's pulling this beam away, right? That's the load that we need to transfer. So how do we get the force? How do we get this force in the beam that's parallel to the wall into the beam that's perpendicular to it? That's what we got to do here. So we need to visualize our load path, right? After all, that's primarily what we're doing here in structural engineering, is making sure that we can follow our load paths and that we can provide adequate resistance each step of the way to ensure that the loads are accounted for. So we've got this force that's pulling the beam out of the structure. How do we get it into, well, it looks like first we need to go into this lag bolt. So how do we get it into the lag bolt? So this here's a lag bolt. If you have a question on that, I'll point you to another tutorial where we cover connectors, but that's our lag bolt. We need to then get this force into this lag bolt. So you need to visualize how this is going to fail. Well, it looks to me like if this were to fail, it would be the lag bolt staying here, if you will, staying put, and uh, the beam would slide out and end up a little bit higher, right? It'll blow out. Kind of what I'm showing you with this blue rectangle, right? It will pull away. In essence, it will pull away from that lag bolt. So that should be a clue, right? What are we designing this lag bolt for? We're designing it for withdrawal. Okay, so we've got a lag bolt with withdrawal, under withdrawal loading. So for that, we would have to, I don't want to get too much into that. That's a matter for another tutorial. But we would need to take into account the lag diameter. We would also need to take into account the embedment of this lag bolt, right? This distance here, the diameter of the lag bolt, and that will dictate then how much withdrawal capacity we have. So with that, we got the load into our lag bolt. Okay, then what's next? Oh, by the way, for whatever it's worth, we do have a value here. Whether it's correct or not, well, that you need to check for your conditions, right? You can see here we have a 5/8 inch bolt that is 3 inches long. Actually, two 5/8 inch bolts that are 3 inches long to resist that load. Maybe that's enough. Maybe it isn't. Maybe you can do with less than that. Maybe you need more than that. That's for you to check. Again, we have other tutorials where we explain how to do the calculation on the lag bolt in withdrawal. So if you need help with that, again, leave us a note there at the end, and we'll try to point you in the right direction. But you do need to check this lag for the withdrawal load. Okay, now let's assume that we've got the load into the lag bolt. Then what? Okay, well, you can kind of see here. Let me use black, and notice how we've got this shape here. Okay, that shape that I just showed you in black is this element here. So that's a 6x6 by 1/4 inch by 6 inch long angle. So what do all those numbers mean? Well, the first 6 refers to one of the legs. That's this dimension. The second 6 refers to the other leg. That would be this dimension here. The 1/4 is the thickness, and the 6 inches, the last 6 inches, this here, refers to the direction in and out of the plane. So in this case, it's in and out of the plane. In the structure itself, it's the vertical direction, right? That's the length of this angle section in the vertical direction. On this particular detail, since this is a plan view, it's the dimension of the angle that goes in and out of the plane. Excuse me. So we got a 6x6 by 1/4 by 6 inch long angle. All right, how do we know that that's adequate? How do we check this member for the forces that we have to make sure that it can resist the forces that are induced on it? Well, here's how I would do this. Let me blow up our angle off to the side here. So this is kind of an exaggerated view of it, right? There's our angle. I'm going to show the lag bolt in red. And remember, that lag bolt has a force that's pulling up. As we're showing this in this sketch, it pulls up on the angle. So what the angle is going to want to do, and this is, again, where it gets where if you will, the artsy part of structural engineering comes in. It's this ability to visualize deformation and being able to visualize failure modes that becomes so essential to what we do. So the way I would visualize this failing is by this leg, by this angle being so weak that it would just pull up like this. Let's see, here it probably would straighten out, right? Or actually would just be straight. It would kind of be curving here, and then it'd be straight over here. Because what do I have there? Well, let me redraw that in a way that's a little bit friendlier maybe to how we would see it in school. There. So does this ring a bell? Right? This is kind of how we saw it in school. We have a cantilever beam fixed on one end, free on the other, with one concentrated load on it, right? This is what we learned in school. Well, this in red. This is real world for what we learned in school, and we were taught in school looks like this. So what we've got is a cantilever beam with a concentrated force. So what's our lever arm? Well, let's see. So here's our distance. So therefore, here's our lever arm. I'm going to say that the cantilever beam is fixed at the other leg. It cantilevers out to the concentrated force. That's the distance. That's what creates the moment then. Therefore, I have a moment. Oh, sorry, can't do that. So I have a moment here that's counterclockwise acting on this leg that in this illustration is horizontal. It's the horizontal leg. And that gives me the moment on that leg. So in essence, what I would be checking for here is a weak axis bending of that steel plate. If you need help with that, let us know at the end of this tutorial, and we'll point you in the right direction. But what you've got is weak axis bending on that plate that I've modeled, that I would model as a cantilever beam, to see if it's adequate to resist the force that the lag bolt induces on it. Okay, with that then, let me go to brown here. Once I do that, then I've now, how do I draw this? I now have an axial load, if you will, going in this leg of the angle, right? This member is now in an axial load. That's probably a force that I'm not going to worry too much about. Got to figure if my angle, remember the thickness of the angle is the same for both legs. So if my angle is adequate for in bending, if it's adequate in bending, and remember it's weak axis bending, then I'm going to figure it's adequate for this axial load. So I'm going to assume we're good there. Then the next thing that I need to check for is the lag bolt that I've got that transfers the load from the angle into, excuse me, into the beam, into this beam here, right? So that would be this lag bolt. That lag bolt is loaded in shear. So now, same thing. I've got to look at the diameter of the lag bolt, and I've got to look at the embedment of the lag bolt. And depending on that, I can design the shear capacity for the lag bolt and ensure that that's adequate to resist the load that I need to transfer. And with that, I've got the load into the beam that then anchors back into the diaphragm. Okay, I think that concludes what we wanted to cover in this tutorial. Let me just make sure of that. Yes, so so if you do have any questions on this, please feel free to leave us a note at the end. We'll try to point you in the right direction or clarify it for you. If this was helpful to you, if you found this helpful, sure would appreciate you giving us a thumbs up. If you have any comments or suggestions, by all means, leave them at the end of this tutorial. That would be appreciated. And if this was helpful to you, then certainly would appreciate if you subscribe to our channel for structural engineering design tutorials. And that way you can be automatically notified whenever we upload tutorials. Okay, real good, guys. Take care.